welcome back. So I hope you got time to develop an opinion as to what will happen if I apply now a Vi, where Vi is equal to 0.1 volt sine omega t. So let's start from the input side. So if Vi is 0.1 volt sine omega t, so this, since I am not drawing any current through this loop, this voltage will also be Vi. So the voltage at the gate, the total voltage at the gate of M1 will be 6 volt plus Vi, right? It will be 6 volt plus Vi. If the total voltage is 6 volt plus Vi, what is the total current flowing through the transistor? The total current flowing through the transistor is 25 milliamps plus Gm times Vi, right? So if this is the total current, what is the total voltage that has developed at the drain? The total voltage will be the quiescent drain voltage, right? So essentially the total voltage will be Vd. Note again, small v, capital D, which means I am trying to figure out the total drain voltage. The total drain voltage is the total current, that is IDS, or rather let me just say VDD minus the total current IDS times RL, right? So VDD is 30 volt, IDS is 25 milliamp plus Gm times Vi times RL, which is 1 kilo ohm, which essentially means that this becomes 5 volt minus Gm RL times Vi. What is Gm RL? Gm RL is nothing but the gain, and gain is 10, right? So this becomes 5 volt minus 10 Vi, right? So this is the total drain voltage. So now what do you think is going to happen? Note that your Vi is 0.1 volt sine omega t, which essentially means that so let me take a different page. What is so my total, so the incremental input is this is the incremental input, this is time, this goes on, this goes on. So this is the incremental input Vi. What is the quiescent input? The quiescent input is 6 volt. So this is, so let's say this is 6 volt, right? I understand this is not to scale, but bear with me. So this is 0.1 volt, right? So this is VGQ, okay? So what is the total? Now if I sketch with respect to time, if I sketch the total drain voltage, what should I get? So let me again point out the fact that total drain voltage is 5 volt minus 10 times Vi, right? So let's sketch the 5 volt first. So let's say this is, use a different color. So let's say this is VDQ, which is 5 volt, right? And this is the quiescent. What is the incremental? The incremental is minus of 10 times Vi, right? So there are two things to notice here. One is the amplitude of the sinusoid, right? So if I write it in terms of sinusoid, what do I get? This becomes Vd is equal to 5 volt minus 10 times Vp sine omega naught t. Note that the amplitude of the sinusoid has gotten multiplied by a factor of 10 if the transistor is in saturation, right? But not only that, there has been a sign reversal, right? There has been a sign reversal, and this sign reversal is the consequence of the fact that I am drawing current out of the load RL, right? Okay, so how should I sketch this? So this minus 10 Vp sine omega t should look like ten times. Oh, let me make this shallower, otherwise it really doesn't make too much sense. So let me make it really shallow, as shallow as I can make without losing the context. Right, so let's assume this is one cycle of that sinusoid and you have repeated cycles. So if I make this 10 times bigger and multiply it minus 1, which means I have to flip the sign of the sinusoid. So if let's say this 10 times bigger means something like this. This clearly is not 10 times, but let's say this is 10 times for the time being. So what will this be? This will be 1 volt. So clearly this cannot be 5 volt, right? I mean, the way I have sketched it, this is clearly I probably will have to bring it a bit up. This is 5 volt. Let me bring this further up. Let's call this 6 volt. Okay. So now do you see a problem? Clearly there is a problem, because now if I see the total gate voltage and the total drain voltage, what do I notice? So the total gate voltage, let's say now I'm plotting the total gate voltage, that is Vg, right? Total gate is VGQ plus Vi, right? So the total gate voltage will be some 6 volt. Let's say this is a 6 volt line. On top of that, I'll have Vi. So this is the total. This is the total gate voltage. And what is the total drain voltage? Again, we are assuming the transistor is always in saturation, and that's why we are drawing all these plots. The total drain voltage is VDQ minus 10 times Vi, right? So I have some 5 volt line here. So let's say this is the 5 volt line, and I'll have okay, fine. So what do you notice here? You notice clearly that when the input is going high, right? If I go back to this, if I go back to this diagram once again, what am I noticing? The thing that I'm noticing is that when the gate voltage is going high, the gate voltage is clearly a sinusoid on top of a DC voltage, right? So this is my gate voltage. So when the gate voltage is going high, what is happening to the drain voltage? So let me remove this. What is happening to the drain voltage? When the gate voltage is going high, the drain voltage is going down. And what is the minimum the drain voltage is going? Or rather, when is the drain voltage going to its minima? The drain voltage is going to its minima when the gate voltage has gone to its maxima, right? So when the gate voltage is at its peak, that is 1.1 volt, the drain, or rather 6.1 volt, what is the drain voltage at? Drain voltage is 5 volt. So let me just remove this line and just call this a 5 volt line. So what is this? If this is 1 volt, so what is the minimum drain voltage? This is at 4 volt, correct? So the drain voltage here is doing just the opposite. The drain voltage is doing like this. So when the gate voltage has gone up to 6.1 volt, the drain voltage has gone down to 4 volts, right? To 4 volts. So now can you comment if this transistor under this condition at this time juncture, is it in saturation, or is it in linear region or triode region? Clearly the transistor here is not in saturation, it's in linear region, right? Because I am not satisfying the condition of VD should be greater than VG minus threshold voltage, right? In other words, the easy way to think about it is that if you know the total gate voltage, you can only allow the drain voltage to go one threshold voltage below the gate. If the drain voltage goes more than one threshold voltage below the gate, the transistor goes out of saturation, right? So clearly, if in this case, when the input has gone to 6.1 volt, the minimum the gate voltage or the drain voltage that is allowed should be 5.1 volt, right? Other than that, you will have a problem. Okay, so what is the solution? The solution clearly is the same old. The transistor is in triode, right? What we need to do, we need to raise the drain voltage, and what is the only handle that we have? The handle that we have is to raise the VD, right? So what is the solution? So in this case, let me write down, since VD, that is the total drain voltage, since VD is less than total VG minus threshold voltage, therefore M1 is in linear region. Solution: increase VDD to ensure VD is always, or rather, let me just say, to ensure VD is greater than equal to VG minus threshold voltage for all values of the input, right? Or what is the worst case situation? The worst case situation is for the maximum amplitude of the input, right? For VG is equal to 6.1 volt, right? So if you can ensure that, then you are good. So what is it? So what will be the value of VDD if we have to ensure that? So I leave it up to you to do this exercise, right? Okay, so let me write it down. Find VDD mean to ensure saturation of M1 for Vi is equal to 0.1 volt sine omega naught t, right? Okay, great. So now let me ask you one more question. What do you think is going to happen? So let me copy this figure once again. So VDD has to be raised. So let's assume you have raised the VDD, right? Let's assume we have raised the VDD. And the transistor is in saturation, which means when this is at 6.1 volt, this minimum voltage is at 5.1 volt, right? So this, let's assume that we have been able to successfully raise the VDD. Okay. So now the question is, I mean, are we all good, or is there any issue? So one might, I mean, you might ask, is that we took care of the condition when the input was rising, right? So what about the case when the input is falling, right? So what about this cycle? What about this cycle? So what is the is there a problem if the input goes low? Clearly, if the input, when the input is going low, when the gate voltage is going low, what is happening to the drain voltage? When gate voltage goes down, when the gate voltage is going down, the drain voltage is going up, right? They are antiphase. The drain voltage is going up. So I am increasing the difference between the drain and the gate. So I am clearly pushing the transistor more and more into saturation. So getting into saturation is not the problem, but is there a problem in the input side? As in, is it at all possible that the transistor is getting cut off, right? So what do you think will be the likely problem? Now one might say that if we apply a negative voltage, negative incremental voltage, right? So the gate to source voltage is reducing. right? So the gate to source voltage is reducing, which essentially means that I am pushing that transistor more and more towards cutoff region, right? I'm pushing the transistor more and more into cutoff region. I'm trying by simply reducing the current further and further, right? So what is the total current? Total current, that is IDS. The total current IDS is IDSQ plus incremental current, correct? So what is the total, what is IDSQ in this case? This is 25 milliamps. What is the incremental current? Incremental current is GM times VP sine omega naught t. Now what needs to happen? What needs to happen in order to push, in order to so rather let me ask you this. What do you think your total IDS will look like? So if I sketch the total IDS, again total IDS is IDSQ plus GMVP sine omega naught t. So let's say this is my 25 milliamp line, right? What is GM? GM is 10 millisiemens, right? GM is 10 millisiemens, and what is VP? VP is 0.1 volt, right? So what is GM times VP? 10 millisiemens times 0.1 volt is 1 milliamps, right? So this is 1 milliamps. So what do you think your IDS will look like? The IDS essentially will look like this. So this will go up by 1 milliamps and it will go down by 1 milliamps. So this is 25 milliamps. So the minimum current will be 24 milliamps and the maximum current will be 26 milliamps. So clearly we haven't applied a large enough VP to completely shut the current off, right? We have only applied a small enough current, a small signal current, right? So that the current does not change at all, right? Okay. So herein comes another question that we have been avoiding till now. That is, what is small signal, right? What is the validity of small signal in a, or rather what is the limits of small signal? What is the limit of small signal in a MOSFET, right? So the answer to that, again one might point out, is dependent on architecture, right? So whatever is small signal for one particular architecture might not be small signal for another architecture. But let's take a vanilla MOSFET into account, right? Let's take a vanilla MOSFET that has been biased in saturation into account and try to make a case for it, right? So let's assume that a transistor is in saturation, right? Let's assume the transistor is in saturation and I have biased it such, right? The same thing that we have done till now, right? and let's say this is VGSQ and this is VI, and this is the VDS is held in such a way that the transistor is in saturation. Okay, so we will try to answer this question in the context of what is small signal as far as the current and the voltage relationships are concerned, right? So in the context of IDSQ, or in the context of IDS versus the input signal, right? So let's quickly do that. So what is IDS? What is the total IDS? Total IDS is half UN Cox W over L BI plus VGSQ minus threshold voltage whole squared, which is half given Cox W over L VGSQ minus threshold voltage whole squared plus half mu n Cox W over L BI squared plus mu n Cox W over L VGSQ minus threshold voltage times Vi. Right? So this is what IDS is. And when we say that we are doing small signal, what are we saying? We are saying that we are neglecting this term with respect to this term, which essentially means that we are assuming half mu n Cox W over L Vi square is much less than mu n Cox W over L VGSQ minus threshold voltage times Vi. So these go off, this goes off, one Vi cancels, right? So essentially we are assuming that Vi should be much less than twice of VGSQ minus the threshold voltage, right? So as long as we can satisfy that Vi is much lesser than twice the overdrive, right? We are good, right? So this is as far as the constraint on small signal is concerned, right? So is the small signal constraint valid in our case? I mean, for example, it's a small signal constraint valid when Vi was 0.1 sin omega t. So in our case, what was Vi? Vi max was 100 millivolt. So Vi max was 0.1 millivolt, 0.1 volt. And what was overdrive? VGSQ minus threshold voltage was 5 volt. And clearly this condition was satisfied. So we could safely assume that small signal approximations are well and good. Okay. So to quickly recap, what did we do in today's lecture? We saw that we started off and saw that what do we need to do in order to ensure that the MOSFET is in saturation, provided obviously the input side has been taken care, right? So we needed to apply a higher VDD, higher supply voltage on the drain side in order to keep the transistor in saturation. Then we said that what we need to do I mean, is something change? Does something change if I apply a sinusoidal input? So clearly, if we apply a sinusoidal input, then it is likely that the transistor might go out of saturation. If you bias the quiescent condition, if you bias the transistor at quiescent condition just at the edge of saturation, because as the signal swings, the drain voltage will also swing, and as it turns out, if the gate voltage increases, the drain voltage decreases, and the transistor goes closer and closer towards linear region and away from saturation. So you need to keep some margin and ensure that under quiescent condition you don't bias your transistor just at the edge, right? And then we try to investigate what happens when the input goes down. When the input goes down, clearly when the input decreases, when the VG decreases, I shouldn't say input because input can be applied anywhere. When the gate voltage decreases, the drain voltage increases, which means the transistor is safely into saturation. However, there is a chance that the transistor current might reduce so much that it completely shuts off, right? So we need to be careful and see whether that is valid or not. And we saw that under the conditions that we used, it seemed to be okay, right? Then we essentially said that what needs to be done in order to first validate whether the small signal approximation that we have been so liberally using in case of a MOSFET is actually valid or not. We had done this limit calculation in case of a diode, which turned out to be twice that of the thermal voltage, and we did the same thing here. And what did we find? We found that as far as the IDS versus VGS characteristics is concerned, the small signal approximation holds good as long as the applied gate to source, incremental gate to source voltage, right? I should actually be more careful, and let me just say that this is, instead of putting VI, let me make it more explicit. Let me call it incremental VGS, because the input has been applied between the gate and the source. So let me modify this as VGS, small VGS, small VGS, small VGS. So we saw that as long as the incremental gate to source voltage is much less than twice the overdrive of the transistor, the approximation of small signal is valid, right? Okay, so let's stop here. We'll see you in the next class.